Okay, so my name is Schmidt. I'm a software engineer, and I picked the topic of introduction of parallelism. I know not everybody here have kind of like a programming background. That is okay. Parallelism is very useful in everyday life aspects as well. It can make you somehow a master of time management skills. So just wing with it. You'll be fine. So okay, what is parallelism exactly? A simple way to say it, just basically, let's just do a couple of things all at once perfectly. And it's a form of computing that performs several steps on multiple processors or processor cores simultaneously. Now we're entering like 8 cores, 16 cores. The cores are getting more and more. And then if we talk about graphic cards, there's even more computational powers. If the power's there, why not utilize it, right? So to not be confused with concurrency, they sound very similar, but how about concurrency? Concurrency creates this illusion of parallelism by basically interviewing operations, and even though the task might not be executed at the same time. So you see here's this pattern where we're kind of jumping around from core 1 and 2, 1, 2, 1, 2. So basically, parallelism is what I want to do when I multitask at work. Concurrency at a very low productive level is what really happens. So there is that. So a very common pattern of how you actually apply parallelism in programming is called a split, apply, and combine pattern. So this little picture here kind of illustrates we're trying to sum all the data to match the key. So instead of actually just writing it in a single thread, we go through the A, B's, and C's and then add them together all in just one thread. We would go ahead and split them based on their keys. And then we would use different threads here to sum them up and then combine them together. So it's like you map it and then you reduce it to exactly what you want. So there are different types of parallelism. There is the ones where you basically look at how big your data is, and then you divide that data, and then we just compute the exact same thing, but in different portions. There's also the task-based parallelism, where you kind of map out what I might really want to do with this data, and then we do 1, 2, and 3, and then combine them together in the end. So what are some challenges of parallel programming? If we can do all these things at once, why don't we just parallel everything, right? No, unfortunately, the world is not that perfect of a place. So first of all, there is this elephant in the room called dependency management. If your task is kind of really intertwined with each other, it is really hard to map out a perfect scenario where you can do everything perfectly. Then you kind of shoot for concurrency. There's also load balancing, which is you're kind of hoping all your tasks will take about the same amount of time through your partitions. If your load is not balanced, you end up actually doing more of a single thread because you kind of put all your other work in one of the heavier load threads. All the others are done and just kind of do it with their thumbs. That's not really efficient. We don't do that. And then there's also the synchronization of overhead. So what that means is you have to actually divide the data and then combine them together. But what if the divide and combine process is actually extremely inefficient? And then in the end, even though you're dividing the work, what really adds up to your efficiency here is the process of putting things apart and then put them back together. And if that takes too long, then it's not worth it. And then in the end, the fourth one is debugging parallel programs. A pain. So you just kind of hope it works exactly how you want it to, but then when there is something that is actually wrong, it is really hard to reproduce the error. So those four togethers, when do you actually want to apply parallelism in your code? So generally, there's 2 signs to look for. One is there are actually just a huge amount of data. If you just have a couple of lines, don't worry about it. Just do it once, it's fine. But when you have a lot of data, if we're talking about a very high resolution image with all those pixels, and then you're gonna do certain things again, maybe let's think about divide that. And then on top of that, you want the tasks to be somewhat more independent among each other. If they're really very intertwined like a web, that's kind of hard to make sure everything can be mapped out efficiently. Then even if it does, we kind of run into the problem where the overhead is really high. So we don't really want that as well. So we have a couple quick examples here to just kind of say like the applications of parallel programming. A very common one is the image and video processing. So if you want to, let's say, apply a filter on a picture, generally speaking, that is a parallel process. And in Adobe or any other applications, in the background, they will divide the picture into several different sections and then apply them through several cores. So you would also notice when you have a slower computer and then a faster computer with a better CPU, more computational power, you notice, oh, this image is actually processing so much faster. I wonder why. And then another big one is crypto, of course. So when you're encrypt and decrypt a large amount of data volumes, you're kind of doing the same thing again and again and again. So it's a really good example to divide that work and then do it parallel at the same time. And of course, machine learning really uses heavily on parallel programming. If you want to do some sort of string tokenization and then sentiment analysis or some sort of topic modeling, and those things, again, require a huge amount of data processing, and it just makes sense to utilize all the computational power to have and then divide them into pieces. I kind of have personally run into the third one where I was using what's called the scikit-learn library, and there is a part of it called a grid search. A grid search is normally very big operation. I remember running it the first time on a virtual graphic card. It took 4 or 5 hours to get it done. And then later we found a library that can basically convert that operation into a multi-thread one. And it shrunk down the time from 5 hours to about 90-something minutes. It was quite amazing. Because the problem is sometimes you don't really even know something wasn't working until 1 hour into it. And then you get a little error. You're like, oh no. So yeah. So that's pretty much it. Thank you.